Everyone walks away from school with the same impression. The universe is impossibly complicated, a tangle of separate rules for separate things, far too much for any one mind to hold. But here is what they never told you. Almost all of it, every flash of lightning, every color in a sunset, the reason your hand does not pass through the table, the reason the sun burns, the reason a magnet grips your refrigerator door, comes from a single equation. One equation, small enough to print on the side of a coffee mug. We have tested it against nature to 12 decimal places, an accuracy like measuring the distance across an entire continent to within the width of a single hair, and in its own domain, it has never once been wrong. And yet the people who wrote it down will tell you, quietly, that it is missing something so enormous that it dwarfs everything the equation contains. What if the most successful law ever written describes only a fraction of what is real? Get comfortable. Hit subscribe if you're new here, because by the end of this, the equation small enough to fit on a coffee mug will look less like an answer and more like a doorway. Now, let's slowly ease into this. Part 1. The equation small enough to fit on a coffee mug. Suppose I told you that there is one equation, just one, that describes almost everything you have ever seen, heard, touched, or measured. Every flash of lightning, every color in a sunset. The reason your hand does not pass straight through the table in front of you, the reason the sun burns, the reason a magnet clings to the door of your refrigerator. All of it packed into a single equation, small enough to print on the side of a coffee mug. You would be right to think I had lost my mind, and yet that equation exists. We have written it down. Physicists have tested it to a precision that is almost difficult to believe. And here is the part that I find genuinely unsettling. That equation is almost certainly incomplete. Something enormous is missing from it. Something so large that, once you understand what it is, you may never look at the night sky in quite the same way again. That is what I want to walk through with you tonight, slowly, with nowhere to be and nothing to rush toward. By the time we are finished, you will understand what that equation actually says, in plain language, with no advanced mathematics required of you at all. You will understand why it is considered the single greatest achievement in the history of physics. And you will understand why, for some of us, it is also the thing that keeps the lights on late, long after we should have gone to sleep. Because what the equation leaves out may turn out to matter more than everything it includes. Let me begin with something simple, something you already know, even if you have never once thought of it as knowledge. You throw a ball into the air, it rises, it slows, it stops for the briefest instant, and then it falls back down into your hand. You have been watching this happen since you were 2 years old. There is nothing remarkable about it. A child does it without thinking. And yet, while that ball is in the air, it is obeying a law. It is not choosing to come back down. It is not deciding to trace a graceful curve through the air. Something is making it do that. And the question I want you to sit with, the question that almost nobody bothers to ask, is simply this. What? If you put that question to Isaac Newton, he would have answered it without hesitation. There is a force pulling the ball downward, he would say, the force of gravity, and my law tells you exactly how it behaves. Force equals mass times acceleration. That is the rule. And it is a wonderful rule. It genuinely works. With Newton's law in hand, you can calculate where the ball will land before it has left your fingers. You can aim a cannon and strike a target you cannot even see. You can fly a spacecraft 250,000 miles across empty space and put it down gently on the surface of the moon. For more than 2 centuries, force equals mass times acceleration was the engine of physics, and it carried us a very long way. But there is a question hiding underneath Newton's answer that always bothered me, even when I was young. Newton tells you that the ball follows one particular path. It goes up along this curve and it comes back down along that one. Fine. But why that path and not some other path? What is so special about the route the ball actually takes compared to all the other routes it could have taken instead? That is a strange thing to ask, and most people never ask it. They say, well, the ball follows Newton's law, and that is why. But notice that this is not really an answer. It is a little like saying the ball does what it does because it does what it does. I wanted a reason underneath the reason, and it turns out, astonishingly, that there is one. It is more beautiful than I can easily express, and the first time you truly understand it, it rearranges something in your mind. The path the ball actually takes is the one path out of every conceivable path that makes a certain number as small as it can possibly be. There is a quantity, a single number, that you can compute along the entire journey of the ball from start to finish. And nature, somehow, selects the journey that makes that number the smallest. We call that number the action, and the rule that nature follows is called the principle of least action. I want you to let that settle for a moment, because it is much stranger than it first sounds, and we are going to spend the rest of our time together unfolding everything that is wrapped up inside it. Notice what I have just said, and what I have not said. I have not told you what force pushes or pulls on the ball at each instant of its flight. I have told you something far stranger than that. I have told you that nature appears to consider every possible path the ball could take, every single one, every lazy arc, every wild zigzag, every loop and detour and impossible diversion. And out of all of them, it keeps the one that makes this special number, the action, as small as it can be. It is as though the ball, before it has even begun to move, somehow surveys all of its options at once and chooses the most economical one. This is a completely different way of thinking about the world than the one Newton handed us. Newton says, look at the ball at this instant. Ask what force is acting on it right now. That force tells you what it does in the next instant. It is a local way of thinking, step by step, moment by moment, the way you might feel your way along a dark hallway with one hand on the wall. But the principle of least action says something else entirely. It says, look at the whole journey at once. Look at where the ball begins and where it ends. Then, among all the possible ways of getting from the one to the other, nature takes the path that makes the action smallest. That is a global way of thinking. It takes in the entire trip in a single glance, as though the beginning already knew about the end. And here is the part that ought to stop you in your tracks. Both of these descriptions give you exactly the same answer. Newton's law and the principle of least action are not rivals. They are mathematically equivalent. They are two different languages describing the very same motion, the way two people might describe the same sunset in two different tongues and mean precisely the same thing. You can start from Newton and arrive at least action. You can start from least action and arrive back at Newton. Neither one is more correct than the other when it comes to a thrown ball. But, and this is the turn on which everything else depends, the principle of least action turns out to be far more powerful than Newton's law. It generalizes in a way that Newton's specific formula simply cannot. Force equals mass times acceleration works beautifully for balls and planets and cannonballs, for anything you can hold or throw or watch fall. But the moment you step into the world of electricity, of magnetism, of light, of atoms, of the forces locked inside the nucleus of an atom, Newton's particular formula stops working. You need different equations for each of those domains, and his does not apply. The principle of least action, though, keeps working. For every single one of them, you only have to change what goes inside the action. You change the recipe, but the principle itself never changes. And that small fact that one idea survives where everything else breaks down is the thread we are going to follow all the way to the equation on the coffee mug. Because if a single principle can quietly underlie all of physics, then the obvious question becomes the one we will spend the rest of the night chasing. What, exactly, is the recipe that describes everything? Let me dwell on that claim a little longer, because I do not want you to nod along politely without feeling how outrageous it really is. The list of things that single equation governs is not a short or careful list. It is nearly everything. The reason a candle flame is yellow and a gas flame is blue. The reason ice is slippery and glass is transparent and metal is cold to the touch. The reason a bruise turns purple and then yellow as it heals. The reason your phone can pull an invisible signal out of the air. The reason the iron in your blood can carry oxygen. And the reason that oxygen burns the sugar in your cells to keep you warm. Every one of those is, at bottom, the same handful of particles obeying the same handful of rules written into that one recipe. When I say one equation describes the world, I am not speaking loosely. I mean it almost literally, and the closer you look, the more literally it turns out to be true. And yet, I keep using that word, almost. Almost everything. Almost literally. That little qualifier is doing an enormous amount of work, and by the end of the night you will see that it hides the most important part of the whole story. For now, simply hold both halves of the paradox in your mind at once. We possess a law of astonishing reach and astonishing accuracy, a law that has never once been caught making a wrong prediction in its own domain. And that same law is, by the honest admission of the very people who wrote it, missing something so large that it dwarfs everything the law contains. How both of those can be true at the same time is the puzzle we are going to unwrap, and it begins, as the best puzzles often do, with something as ordinary as a ball falling back into your hand. Part 2. The one idea underneath all of physics. Let me say plainly what I only hinted at a moment ago, because it is worth repeating slowly. The principle of least action is the single idea that underlies all of physics. Not most of physics, all of it. All of classical mechanics, the physics of balls and planets, all of electricity and magnetism, all of Einstein's theory of gravity, which we will come to. All of quantum field theory, the strange and powerful framework that describes the particles inside the atom. Every fundamental theory we have ever discovered obeys this one principle. And here is what makes that remarkable rather than merely tidy. We did not demand it in advance. Nobody sat down and decreed that nature must work this way. Nature showed it to us, again and again and again, in field after field, until it became impossible to ignore. Every time we have dug down to the foundations of a new piece of physics, the principle of least action was already there, waiting. I want to take a small detour here, because this idea has a history, and the history tells you something true about the way physics actually moves forward, which is almost never in a straight line. The first person who really saw this principle was a Frenchman named Pierre-Louis de Maupertuis, working in the 1740s. He had a somewhat mystical reading of it. He believed that God, being perfect, would naturally have designed a universe that wasted no effort, a universe that always did things in the most economical way possible. That was his reasoning. It was not very scientific, and we would not phrase it that way today. But he had the right instinct, even if he had wrapped it in the wrong clothing. He sensed that nature was, in some sense, frugal. After him came better mathematicians. Leonhard Euler and Joseph Louis Lagrange took Maupertuis's hazy intuition and put it on firm mathematical ground, building the machinery that lets you actually compute these things, a branch of mathematics now called the calculus of variations. And by the 1830s, an Irishman named William Rowan Hamilton had turned the whole thing into a complete and elegant framework, the version we still teach today. But here is the funny part, the part that I think is genuinely instructive. For a very long time, physicists treated the principle of least action as little more than a curiosity, a clever reformulation, a pretty piece of mathematics that was nice to know but practically useless. Newton's force equals mass times acceleration was the workhorse. You had a force, you computed the acceleration, you solved the equation, and you went home. That was physics. The approach built on the action, the so-called Lagrangian approach, was considered a kind of intellectual luxury, a decoration. And then, in the 20th century, everything turned over. It turned out that the Lagrangian approach was not a luxury at all. It was the only approach that worked for the new physics that was arriving. When you try to write down the laws of electricity and magnetism, or Einstein's theory of gravity, or the quantum theory of particles, in Newton's old language, the whole thing becomes a nightmare. The equations grow tangled. The beautiful underlying symmetries are hidden from view. The structure is obscure, like trying to read a poem with half the words smudged out. But in the language of the action, in the Lagrangian language, everything becomes clear. The symmetries stand out in plain sight. The structure is transparent, and the ways to extend the theory, to push it into new territory, practically leap off the page at you. It was as though, for 200 years, we had been building houses with nothing but a hammer, and then one day someone handed us a power drill, and suddenly we could build towers. The Lagrangian formulation was the power drill of modern physics. Nearly every major advance of the 20th century was built with it. And it all traces back to that one simple, almost childlike question: what quantity does nature make smallest? So now you are surely wondering what this action actually is. What is the thing inside it? What is the recipe? Let me tell you, gently, because it is simpler than you might fear. The action is computed from something called the Lagrangian. The Lagrangian is a function, a recipe if you like, that tells you at every point in space and at every moment in time what the system is doing. For a ball flying through the air, the Lagrangian is almost shockingly simple. It is just the kinetic energy minus the potential energy. Kinetic energy is the energy of motion, the energy a thing has because it is moving. Potential energy is the energy of position, the energy a thing has because of where it is, like how high up it sits above the ground. You take that difference, kinetic energy minus potential energy, at every instant along the path, and you add it all up across the entire journey. That running total is the action. And nature, faithfully, makes it as small as it can be. Now, I want to be honest with you about where we are headed, because the simple ball was only ever the doorway. What I have described so far is classical physics. It is beautiful, and it is true within its domain, but it is also old news, the physics of 2 centuries ago. The thing that genuinely shakes you, the thing I have been building toward, is what happens when you stop asking about a single ball and start asking a far more ambitious question. What is the Lagrangian? What is the recipe that describes not just balls and planets, but everything, every particle that exists, every force there is, every interaction in the entire universe? Is there a single recipe for all of it? That is the question that the whole 20th century of physics was secretly chasing. And before I can tell you the answer, I have to tell you the story of how we got there. Because the path to that one equation runs through one of the most thrilling adventures in all of science, the long campaign to unify the forces of nature to show that things which look completely separate are secretly the same. And you cannot feel the full weight of the ending unless you have lived through the beginning. So let me take you back, a little more than a century and a half, to a quiet man with a pen and a handful of equations who went looking for a connection between two ordinary things and accidentally discovered what light is. I want to press on the strangeness of this a little more, because familiarity can dull it, and it should not be dulled. Think again about what the principle of least action is actually claiming. It is not claiming that the ball feels a push at each instant and responds to it, which is the picture almost everyone carries in their head. It is claiming that the entire path, from the first instant to the last, is selected as a whole, judged against every alternative path by a single number. The beginning of the journey behaves as though it already takes the end into account. In Newton's local picture, the ball is like a person walking through fog, feeling forward one step at a time, with no knowledge of the destination. In the action picture, it is as though the whole route were laid out on a map and the best one chosen before the first step was taken. These are radically different stories about how the world works, and the unsettling thing is that, for a thrown ball, they are exactly equally true. For 200 years, most physicists treated this equivalence as a curiosity precisely because, for ordinary objects, it does not matter which story you tell. You get the same answer either way, so why trouble yourself with the stranger version? But nature was quietly hinting at something, and the hint was this: the local story and the global story are equally true for a ball, but only the global story survives when you descend into the world of the very small. The principle of least action was not just an elegant alternative, it was a message from the foundations of reality, written in a language we would not learn to read until the 20th century. And to read it, we first had to discover what the action was actually made of, the recipe hiding inside it. Part 3. The Recipe and the Power Drill. Before we travel back to that quiet man and his equations, I want to make sure one idea is firmly in your hands, because everything else we do tonight will rest on it. The whole of fundamental physics, as we currently understand it, can be written in a single style. You name the ingredients of the world. You write down one Lagrangian, one recipe that captures how those ingredients move and interact. And then you feed that recipe into the principle of least action, and out come the predictions, the actual numbers you can compare against an experiment. That is the entire machine. Ingredients in, one recipe, one principle, predictions out. If you hold on to that shape, the rest of the night will feel less like a lecture and more like watching a single idea grow up. Let me linger for a moment on why the Lagrangian language won, because it tells you something about what physicists actually mean when they call an idea powerful. Imagine you wanted to describe how water flows through a city. You could, in principle, track every single water molecule, one at a time, noting the force on each one at every instant. That is the Newtonian spirit, local and step by step, and for a glass of water it might even be possible. But for a whole city, it would be hopeless. And worse, it would hide the very thing you cared about, which is the overall shape of the flow. The Lagrangian approach is like stepping back and describing the flow all at once, as a single pattern with its own symmetries and its own logic. You lose nothing in accuracy, you gain everything in clarity. And it turns out that when you write nature this way, the hidden symmetries that we will come to in a little while become visible, and those symmetries are not decoration. They are the scaffolding that holds the entire structure up. There is a reason I keep returning to that word, recipe, rather than something grander. A recipe is humble. It does not explain why bread is delicious. It just tells you, faithfully, what to combine and in what proportion, and if you follow it, you get bread. The Lagrangian is exactly that kind of object. It does not pretend to explain why the universe exists, or why there is something rather than nothing. It simply lists what the world is made of and how those pieces respond to one another. And if you follow it through the principle of least action, you get the universe, or at least the part of it we can presently describe. The miracle is not that the recipe is profound in its wording. The miracle is that there is a recipe at all, that the world is the kind of thing that can be captured by a finite list of ingredients and a single rule. Now, I told you that for a ball, the Lagrangian was simply the kinetic energy minus the potential energy. You might reasonably ask why that particular combination, kinetic minus potential, rather than, say, kinetic plus potential, which would look more natural to most people. And the honest answer is that this is one of those places where nature has quietly told us how things are, and we have learned to listen. If you write down kinetic energy minus potential energy and demand that the action be made stationary, you get exactly Newton's laws back out, every time, with no exceptions. So we know the recipe is right, not because it looks pretty, though it does, but because it reproduces reality. That is always the final court of appeal in physics. Not elegance, not intuition. Agreement with what actually happens when you go and look. And here is the thing that turns a curiosity into a revolution. The very same structure, an action built from a Lagrangian, made stationary by nature, carries over completely intact when you leave the world of balls behind. When you want to describe light, you write down a different Lagrangian, one built not from the position of a ball, but from the electric and magnetic fields filling space. When you want to describe the particles inside the nucleus, you write down yet another Lagrangian, built from quantum fields. The ingredients change, the recipe changes, but the principle, make the action stationary, never changes at all. It is the one fixed point as you climb from the everyday world down into the foundations of matter. And every time physicists found a new layer of reality, they reached for this same tool, and it fit. That is why I called it the power drill. A hammer can drive a nail, and Newton's law can handle a ball. But when you need to raise a structure as intricate as the modern picture of matter and force, you need a tool that works the same way at every scale, in every material, and the action principle is that tool. So we arrive at the doorstep of the real story with our instrument in hand. We know that physics, at bottom, is the search for the right Lagrangian. We know that whatever that recipe turns out to be, the principle of least action will turn it into predictions. The only question left, the enormous question, is what the recipe for everything actually contains. And the answer was assembled, piece by piece, over roughly a century, by people who mostly were not trying to find a theory of everything at all. They were trying to solve smaller, more concrete puzzles, and each time they solved one, they discovered that two things they had believed were separate were in fact one thing wearing two masks. That process has a name. We call it unification. And the first great act of unification, the one that set the pattern for all the rest, belongs to a Scotsman in the 1860s, who sat down to understand magnets and electric currents, and walked away holding the secret of light itself. Let me show you how he did it, because the gift he received from his own equations is one no one had thought to ask for. There is something else worth saying about why this style of physics matters so much, beyond mere convenience. When you write the laws of nature as a single Lagrangian, the symmetries of the world are not hidden away inside the equations where you have to dig for them. They sit right on the surface, plain to see. And, as we will discover in a little while, those symmetries are not incidental. They are the very thing that determines what forces can exist and how the particles must behave. So the Lagrangian language does not merely make the calculations cleaner, it puts the most important structural truths of physics where you can actually look at them. A physicist reading a Lagrangian can often tell, at a glance, what conservation laws the theory will obey and what forces it must contain before doing a single calculation. That is an enormous amount of insight to carry in such a compact form. And I want to return, just for a moment, to that small puzzle of the minus sign, kinetic energy minus potential energy, because it carries a lesson. When most people first meet that combination, they expect a plus sign, the total energy, which feels more natural and more meaningful. But nature chose the difference, not the sum. And we know this not from any prior reasoning, but because the difference is what reproduces the world. This is the humility at the center of physics. We do not get to decide what the recipe should be on grounds of taste. We propose, nature disposes, and the only judge is whether the predictions match what actually happens when you go and measure. The minus sign is correct because the ball lands where the minus sign says it will. That is the whole of the argument, and it is enough. Part 4. Maxwell and the light that fell out of the equations. In the 1860s, a Scottish physicist named James Clerk Maxwell did something that I still consider one of the most extraordinary feats of thought in the history of our species. To understand what he did, you have to understand what the world looked like before he did it. At that time, people knew about 3 separate things, and they regarded them as 3 separate things. They knew about electricity, the spark, and the current, and the charge. They knew about magnetism, the lodestone, and the compass needle, and the strange, invisible influence that turned it. And they knew about light, the oldest and most familiar phenomenon of all, the thing that let them see. 3 phenomena, 3 separate sets of experiments, 3 separate chapters in any textbook of the day. Nobody had any strong reason to think they had much to do with one another. Electricity was electricity. Magnetism was magnetism. Light was light. Maxwell sat down with everything that was known about electricity and magnetism, all the careful experiments of people like Michael Faraday before him, and he distilled it into 4 equations. Just 4. And those 4 equations did something that none of the individual experiments had quite made plain. They described electricity and magnetism not as 2 separate forces, but as 2 aspects of a single thing, a unified electromagnetic field. An electric current could produce a magnetic effect. A changing magnetism could produce an electric one. The 2 were woven together so tightly that you could no longer sensibly speak of one without the other. This, by itself, would have made Maxwell one of the great physicists of his century. But it is not the part that gives me chills. The part that gives me chills is what happened when he sat back and looked at what his own equations were telling him. When Maxwell solved his equations, he found that they permitted a particular kind of disturbance. If you wiggled an electric field, it created a magnetic field. And that changing magnetic field created an electric field a little further along. And that one created a magnetic field further along still. The 2 fields kept handing the disturbance back and forth between them, leapfrogging forward through space, sustaining one another as they went. In other words, his equations predicted a wave made not of water or air, but of oscillating electric and magnetic fields, propagating through empty space all on its own. And here is where it becomes almost unbearably beautiful. Maxwell could calculate, directly from his equations, how fast that wave should travel. The speed was determined entirely by quantities you could measure on a laboratory bench, the strength of electric and magnetic effects, numbers that had nothing obviously to do with light at all. And when he put those numbers in and turned the crank, the speed that came out was about 186,000 miles every second. Roughly 300,000 kilometers per second. Now, that number was already famous. It was the measured speed of light. People had measured how fast light travels, and here was Maxwell, working purely from electricity and magnetism, with no light in his equations anywhere, arriving at exactly that speed. The conclusion was inescapable, and it must have been staggering to be the first person in history to see it. Light is an electromagnetic wave. The thing that lets you read these words, the thing that pours out of the sun, the thing that has been the symbol of knowledge and goodness in every human culture, is nothing other than rippling electric and magnetic fields, travelling at the one speed his equations allowed. Maxwell had not set out to explain light. He had set out to understand the relationship between electricity and magnetism, and light fell out of the mathematics as a gift, a free bonus he had never asked for and could not have anticipated. I want you to hold on to that, because it is a pattern we are going to see again and again as the night goes on, and it carries a kind of hope inside it. When you successfully unify two things that looked separate, you very often get more than you bargained for. The unification pays you back with interest. Maxwell unified electricity and magnetism, and the universe handed him light. It is as if nature rewards the act of finding hidden connections by revealing still more profound ones you did not know to look for. And this is not mysticism. It happened, on paper, with numbers, and every piece of technology that touches electromagnetism, which is to say nearly all of it, stands as proof that he was right. But there is something else hiding in Maxwell's triumph, something that matters for where we are going. When you write Maxwell's theory of electromagnetism in the most natural and powerful form, you do not write it as four separate equations at all. You write it as a Lagrangian. You write down one recipe for the electromagnetic field, you feed it into the principle of least action, and all four of Maxwell's equations come tumbling out as a consequence. The same tool we used for the ball, the same principle Maupertuis, Half-Saw, and Hamilton perfected, turns out to be exactly the right language for light. So the thread holds. One principle, a new recipe, and an entire domain of physics, electricity, and magnetism, and light together falls into place. Maxwell had unified three of the great phenomena of nature into one. The obvious next question, the one that would consume the following century, was whether the trick could be repeated. Were there other forces in nature waiting to be shown as secretly the same? And if so, how far could the unification go before it ran out of room? The answer, when it came, would require us to first count the forces of nature carefully and to discover that there were not three of them, but four. To feel the full size of Maxwell's achievement, it helps to know a little about the man whose work he built upon, Michael Faraday. Faraday was a bookbinder's apprentice with almost no formal mathematical training, and yet he had one of the finest physical imaginations in the history of science. It was Faraday who first pictured the space around a magnet or an electric charge as filled with invisible lines of influence, what we now call a field, threading through the apparently empty room. Most physicists of the day found the idea vague and unmathematical and preferred to think of forces leaping instantly across empty space. Maxwell's genius was to take Faraday's intuitive picture of fields seriously and to give it the precise mathematical form Faraday himself could not. The fields became real and calculable, and once they were calculable, they could be solved, and once they were solved, light came tumbling out. A self-taught bookbinder's intuition and a mathematician's rigor met, and between them they explained the oldest phenomenon in human experience. There is one more thing I want you to take from Maxwell's story, because it will matter at the very end of the night. The fields he described were not just a bookkeeping device. They were a new kind of thing in the world, as real as matter, carrying energy and momentum across space on their own. When you feel the warmth of sunlight on your face, you are feeling energy that left the surface of the sun 8 minutes ago and travelled here as a ripple in Maxwell's fields, with nothing in between to carry it. The idea that empty space is not empty at all, but is filled with fields that can hold energy and carry influence, is one of the great conceptual turns in physics, and it returns later in our story in an even stranger form when we meet a field that gives the particles their mass. Faraday planted that seed, Maxwell grew it. And the rest of physics has been living in the orchard ever since. Part 5. Four Forces and the Second Great Unification. Let me now do the counting that Maxwell's success makes necessary. By the middle of the 20th century, after a great deal of careful work, physicists had identified four fundamental forces of nature. Not three, four. And I want to introduce them to you the way you might be introduced to four very different people at a gathering, because their personalities really are that distinct. The first is gravity, the one you know best in your body, the force that holds you in your chair and keeps the planets circling the sun. The second is electromagnetism, Maxwell's force, the one responsible for electricity, magnetism, light, chemistry, and the simple fact that solid objects feel solid. The third is the strong nuclear force, which holds the nucleus of every atom together against the furious electrical repulsion of the protons crammed inside it. And the fourth is the weak nuclear force, which is responsible for certain kinds of radioactive decay, such as the moment when a neutron transforms itself into a proton, an electron, and a ghostly particle called a neutrino. These four forces seemed, on first acquaintance, to have nothing in common. Consider how differently they behave. Gravity reaches across the entire universe, but it is astonishingly feeble. You can defeat the gravity of the entire Earth with a small magnet, lifting a paperclip off the floor against the pull of the whole planet. Electromagnetism also reaches across enormous distances, but it is enormously stronger than gravity. The strong force is more powerful still, the strongest of them all, but it has almost no reach at all. It operates only across distances smaller than the nucleus of a single atom, and beyond that, it simply vanishes. The weak force is both feeble and short-ranged, a quiet and limited thing. So there they were, four forces, four different strengths, four different ranges, four utterly different characters. It looked, frankly, like nature had simply thrown four unrelated ingredients into the pot and stirred. But by this point, physicists had learned the lesson Maxwell taught them. When two things look separate, do not assume they are. Look harder. And in the 1960s, three physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, working partly together and partly apart, looked harder at two of these four forces, electromagnetism and the weak nuclear force, and discovered something that no one watching from the outside would ever have guessed. Those two forces, which could hardly look more different, the familiar electromagnetism of light and magnets and the obscure weak force of radioactive decay, are actually the same force. At the energies of everyday life, they appear distinct, the way ice and steam appear to be entirely different substances, even though both are nothing but water. But at very high energies, the kind of energies that filled the universe in its first instance, the two merge seamlessly into a single thing, which we call the electroweak force. The reason they look so different to us, down here in the cold and quiet of the present-day universe, comes down to a field that fills all of space, a field I will tell you much more about later, called the Higgs field. The Higgs field is what breaks the symmetry between them. It is what splits the unified electroweak force into the two separate pieces we actually observe. On one side of the split, you get electromagnetism, carried by a massless particle, the photon, the particle of light. On the other side, you get the weak force, carried by three very heavy particles, named, rather unromantically, the W+, the W-, and the Z. The heaviness of those weak force particles is exactly why the weak force is so feeble and so short-ranged, while the masslessness of the photon is exactly why electromagnetism reaches across the universe. The difference in their personalities, which seemed so fundamental, turns out to be a consequence of the Higgs field. Underneath, they are one. This was the second great unification, and notice what it accomplished. Maxwell had already taken electricity and magnetism, two forces, and shown them to be one. Now, the electroweak theory took that combined electromagnetic force and the weak force and showed those to be one as well. The count was dropping. What had looked like separate forces were collapsing into each other. And, just as with Maxwell, the unification did not merely tidy up what was already known. It made a prediction. The theory said that those heavy weak force carriers, the W and the Z particles, must exist, and it predicted, with real precision, how heavy they should be. At the time, no one had ever seen them. They were a promise written in mathematics. And then, in the early 1980s, At the laboratory called CERN, straddling the border between France and Switzerland, the experiments were done at last, the energies were reached, and there they were, the W and the Z, appearing in the detectors at very nearly the exact masses the theory had foretold. The W weighs in at around 80 times the mass of a proton, the Z at around 90, predicted on paper, then found in the world. So now the question almost asks itself, and you can feel the pull of it. If electricity and magnetism became one, and if that result then merged with the weak force to become one electroweak force, can we go further still? Can we unify the electroweak force with the strong nuclear force and bring 3 of the 4 forces under a single roof? And then, in the ultimate dream, can we somehow fold gravity in as well and write down one law for all 4? That is the impossible dream, and we will face it squarely before the night is through. But to even approach it, we first need to look directly at what was actually built, the great synthesis that brought together everything except gravity into a single recipe. It has a plain and almost disappointing name. We call it the Standard Model. And the recipe, at its center, the Lagrangian of the Standard Model, is the equation I promised you at the very beginning, the one small enough to fit on a coffee mug. Let me slow down on the weak force for a moment, because it is the least familiar of the 4, and yet it touches your life more than you might guess. The weak force is what allows one kind of particle to change into another. When a neutron, sitting inside a nucleus, transforms into a proton, it does so by the weak force, spitting out an electron and a neutrino in the process. That single kind of transformation is the engine behind a great deal of the universe's behavior. It is part of how the sun burns, because turning hydrogen into helium, the reaction that powers every star, requires protons to convert into neutrons along the way, and only the weak force can make that conversion happen. So the weak force, feeble and short-ranged and obscure as it seems, is quietly responsible for sunlight. Without it, the sun would not shine, and you would not be here to wonder about any of this. It is worth pausing, too, on just how strange it was to suggest that electromagnetism and the weak force were secretly the same. Think about how different they appear. Electromagnetism gives us light, electricity, magnetism, the binding of every atom, the whole visible texture of the world. The weak force gives us a particular kind of radioactive decay, and very little that you would ever notice directly. One is everywhere and obvious. The other is hidden and rare. To claim that these two are the same force, merely wearing different masks because of the Higgs field, was an act of real intellectual daring. And the only reason anyone believed it was that the mathematics demanded it, and then, crucially, the predicted particles showed up exactly where the theory said they would. That is the pattern of physics in miniature. A bold claim, a precise prediction, and then nature stepping in to settle the argument. Part 6. The equation on the mug, and a number tested to 12 decimal places. Let me be honest with you about what this equation looks like, because I do not want to oversell it and then have you feel cheated when you finally see it. When the Standard Model Lagrangian is written out in full, it is not simple to look at. It fills perhaps half a page with dense mathematical symbols, Greek letters, subscripts and superscripts, summation signs, the whole intimidating apparatus that makes most people close the book and walk away. If you printed it on a coffee mug, you would need a steady hand and small type. So, when I say it is small enough to fit on a mug, I do not mean it looks like 1 + 1 = 2. I mean something more surprising than that. I mean that, despite how forbidding it appears, its underlying structure is so orderly, so tightly organized, that I can tell you everything it says in plain words, and you will understand it. The Standard Model Lagrangian tells you 4 things, only 4. First, it tells you what particles exist, the complete list of the fundamental ingredients of matter. Second, It tells you what forces exist, the ways those ingredients can push and pull on one another. Third, it tells you exactly how each particle interacts with each force, who feels what. And fourth, it tells you how the particles come to have mass at all. That is the entire content of the equation. Those four statements, written in the compressed language of mathematics and fed into the principle of least action, give you every prediction we have ever made about the behavior of matter and energy, with one exception, gravity, which we will return to. And here is the staggering part. Every one of those predictions, every single one that has ever been tested, has turned out to be correct. Some of them correct not to 2 or 3 decimal places, which would already be impressive, but to 10, 11, and 12 decimal places. The Standard Model is, by a wide margin, the most precisely tested theory in the history of science. Let me give you one example, because abstract claims of precision do not land until you feel them. Consider the electron, the little particle that whirls around the nucleus of every atom and carries electric current through every wire in your home. The electron has a property that makes it behave, in a sense, like an unimaginably tiny magnet. Physicists measure the strength of this little magnet with a number, and there is a famous early prediction for what that number should be. An equation written by Paul Dirac in the 1920s, the equation that first married quantum mechanics to Einstein's special relativity, predicts that the electron's magnetic strength should be exactly 2 in the natural units physicists use. Exactly 2. A clean, whole number. But when you go and measure it with exquisite care, the answer is not exactly 2. It is just slightly more than 2. The difference is tiny, a matter of roughly 1 part in 1,000. And you might think, well, so much the worse for the theory, it missed. But this is where the Standard Model reveals its true power. That tiny excess above 2 is not a failure. It is a prediction in its own right. It comes from the fact that the electron, as it sits there quietly being an electron, is never truly alone. It is constantly emitting and reabsorbing a swarm of fleeting, ghostly particles, virtual photons flickering in and out of existence around it, virtual pairs of particles and antiparticles appearing and vanishing faster than anything could ever observe. All of that restless quantum activity nudges the electron's magnetic strength upward by a precise amount, and using the Standard Model, you can calculate that nudge. When you carry out that calculation and compare it against the measured value, the theoretical prediction and the experimental measurement agree to better than 1 part in 1,000,000,000,000. Let me try to give that number a body you can feel. Imagine measuring the distance from New York to Los Angeles, around 2,500 miles, and getting it right to within the width of a single human hair. That is the level of agreement between what the Standard Model predicts and what nature actually does for this one property of this one particle. I do not know of any other theory in any field of human knowledge that makes a prediction that fine and then turns out to be right. When people ask me why physicists hold the Standard Model in such reverence, despite everything it leaves out, this is the answer. This is what the equation on the coffee mug can do. And so you might think the story should end here. In triumph, we have the recipe. We have tested it to 12 decimal places. We have won. But I told you at the very beginning that this equation keeps me up at night, and a theory that simply worked would not do that. To understand both why it is so glorious and why it is so troubling, we have to open it up and look at its pieces. We have to meet the particles it describes, understand how it says forces actually work, and uncover the single most beautiful idea inside it, the idea of symmetry, which is the real engine humming away beneath the mathematics. So, let me introduce you to the cast of characters, the complete list of things the universe is made of. There are remarkably few of them, and that fewness is itself one of the quiet wonders of modern physics. I want to give you one more way to feel the precision of the Standard Model, because numbers like 1 part in a trillion can slide past without landing. Suppose you were measuring not a distance but a span of time. 1 part in a trillion, applied to time, would mean keeping a clock so accurate that it would not gain or lose a single second in more than 30,000 years. The agreement between the theory of the electron's magnetism and the measured value of the electron's magnetism is finer than that. We are not talking about a theory that is roughly right, or right in spirit, or right within the usual margins of science. We are talking about a human-made equation that tracks the behavior of nature so closely that the difference between prediction and reality is smaller than almost any quantity people ordinarily measure at all. And this precision was not a single lucky hit. The same equation predicts the rates at which unstable particles decay, the exact patterns of particles that spray out of high-energy collisions, the precise way light scatters off electrons, and 1,000 other quantities, and it gets them right, over and over, across decades of ever more demanding experiments. Whole careers have been spent trying to find a single place where the standard model clearly fails within its own domain, because a clear failure would be a doorway to new physics, and a Nobel Prize most likely waits behind that door. And yet, within the territory it claims, the equation has held. Every serious challenge has dissolved on closer inspection. That track record is exactly why physicists trust it, and exactly why its enormous silences, the things it does not even attempt to describe, are so haunting. A theory this accurate has earned the right to be taken seriously, even when it tells us, by its silence, how much we still do not know. Part 7. The cast of the universe, and forces you can throw. Let me show you the ingredients, and I think you will be surprised by how short the list is. The first part of the standard model is the particles of matter, the things the world is actually built from. And there are only 12 of them. To impose a little order, physicists sort these 12 into 2 families. The first family is called the quarks, and there are 6 of them, with names that I promise I am not inventing. They are called up, down, charm, strange, top, and bottom. Physicists, it must be admitted, are not gifted at naming things. The second family is called the leptons, and there are 6 of these as well. The most familiar lepton by far is the electron. Alongside it sit 2 heavier cousins, called the muon and the tau, and each of the 3 comes paired with its own kind of neutrino, that faint, nearly weightless particle I mentioned earlier. 6 quarks and 6 leptons, 12 particles of matter in total. That is, the complete inventory. Now, here is something I find genuinely moving, and I want you to sit with it for a moment. Everything you have ever seen or touched, every atom, in every molecule, in every star and stone and living creature, every cell in your own body, is built from just 3 of those 12 particles. The up quark, the down quark, and the electron. That is all. Protons and neutrons, the heavy occupants of the atomic nucleus, are each just bundles of up and down quarks. Wrap some electrons around them, and you have atoms, and from atoms you can build everything in the visible world, from a mountain to a thought. The other 9 particles are heavier copies, exotic relatives that flash briefly into existence in the violence of particle collisions or in the upper atmosphere, and then decay away within fractions of a second. The ordinary world, the one you live in, runs on just 3 ingredients. There is something almost unreasonably elegant about that. The second part of the standard model is the forces, and here the picture becomes genuinely strange and wonderful. In the standard model, forces are not vague pushes and pulls that somehow reach across empty space. Forces are carried by particles. The force itself is an exchange. Let me give you the image that physicists use, because it makes the idea concrete. Picture 2 ice skaters facing each other on a frozen lake, gliding slowly apart. One of them holds a heavy basketball and throws it to the other. In the act of throwing, the first skater recoils backward, pushed away by the throw, and when the second skater catches the ball, she too is pushed backward by its impact. The two skaters drift apart. From a distance, with the ball moving too fast to see, it would look as though some invisible force were pushing the two skaters away from each other. But there is no mysterious force. There is only the exchange of the ball. That is essentially how forces work at the level of particles. Particles push and pull on one another by tossing other particles back and forth between them, and that exchange is what we experience as a force. So each of the three forces in the standard model comes with its own carrier particles, its own basketballs. The electromagnetic force, the one that binds electrons to nuclei and gives us light and chemistry and the solidity of matter, is carried by the photon, the particle of light itself. The strong nuclear force, the one that glues quarks together inside protons and neutrons, is carried by particles charmingly named gluons. Because they glue, there are 8 distinct kinds of gluon. And the weak nuclear force, responsible for radioactive decay, is carried by those 3 heavy particles we already met, the W+, the W-, and the Z. Count them up, and you have 1 photon, 8 gluons, and 3 weak force carriers. 12 force-carrying particles, mirroring, by coincidence, the 12 particles of matter. The world, at its foundations, is a remarkably small zoo. But now we come to the third part of the standard model, and this is where, for me, the real magic lives. The equation does not just list the particles and the forces. It tells you, with almost no freedom at all, exactly how they interact. Which particle feels which force, and how strongly, and in what manner. And the astonishing thing is that these interactions are not arbitrary. Nobody got to choose them by hand. They are dictated, completely and rigidly, by a single idea. That idea is symmetry. When I first understood that the forces of nature are not separate facts you have to memorize, but consequences of a more fundamental principle of symmetry, it changed the way I saw the entire enterprise of physics. So I want to slow down and explain what a physicist means by symmetry, because it is not quite what the everyday word suggests, and it is the most beautiful thing in the whole story. To do that, I need to tell you about a theorem proved by one of the greatest mathematicians of the 20th century that ties the symmetries of the world directly to the things in the world that never change. There is a strange and important fact about the quarks that I cannot leave out, because it is one of the most counterintuitive things in all of physics. You will never, ever see a quark on its own, not in any experiment, not under any conditions we can create. The quarks are permanently locked up inside the protons and neutrons and other particles they compose, and the strong force that binds them has a peculiar character that grows stronger as you try to pull them apart, not weaker. With every other force you know, the influence fades with distance. Pull 2 magnets apart and the attraction weakens. But try to separate 2 quarks, and the strong force between them grows, like a stretching band that pulls harder the further you stretch it. Pull hard enough, and instead of the quarks coming free, the energy you have poured in simply creates new quarks out of empty space, which pair up with the originals so that you end up with more bound particles and never a single free quark. This permanent imprisonment is called confinement, and the theory predicted it before the experiments confirmed it. The neutrinos deserve a word of their own as well, because they are the ghosts of the particle world. A neutrino barely interacts with anything at all. As you sit listening, trillions upon trillions of neutrinos from the sun are streaming through your body every second, passing through you, through the chair, through the entire Earth, as though none of it were there. Most of them will cross the whole planet without touching a single atom. They are so reluctant to interact that it took decades even to prove they existed, and their properties remain among the least understood in all of physics. Hold on to the neutrinos, because near the end of the night, they will return as one of the small but telling cracks in our great equation. The original Standard Model insisted they had no mass at all, and the neutrinos, quietly, turned out to disagree. Part 8. Symmetry and the reason energy can never be destroyed. Let me explain what a physicist means by symmetry, because the everyday meaning, a butterfly's matching wings, a balanced face, is only the shadow of the real idea. In physics, a symmetry is something you can do to a system that leaves its behavior unchanged. Suppose you perform an experiment in your laboratory and you get a certain result. Now pick up the entire laboratory and move it 10 feet to the left and run the experiment again. Do you get a different result? Of course not. The laws of physics do not care where your laboratory sits. That indifference, that sameness under a shift in position, is a symmetry. We call it translational symmetry, the symmetry of place. Now rotate your whole laboratory by 30 degrees and run the experiment once more. Same result again. The laws of physics do not care which direction your equipment is facing. That is rotational symmetry, the symmetry of orientation. Now wait 5 minutes, then repeat the experiment. Same result yet again. The laws of physics do not change from one moment to the next. That is time symmetry, the symmetry of when. These are the obvious symmetries, the ones almost everyone would agree must hold. But I have not yet told you the punchline, and the punchline is one of the most profound results in all of theoretical physics. In the early 20th century, a brilliant German mathematician named Emmy Noether proved a theorem so profound that it quietly reshaped how physicists understand the world. Noether's theorem says that every continuous symmetry of the Lagrangian corresponds to a conservation law. Every symmetry. A quantity that stays fixed, that is conserved, that nature never lets change. And this is not a vague, poetic statement. It is exact, mathematical, and provable. Let me show you what it gives us, because the results are things you already know, suddenly revealed to have a secret source. Translational symmetry. The fact that the laws of physics do not depend on where you are, gives you, through Noether's theorem, the conservation of momentum. The reason a moving object keeps its momentum, the reason a rolling ball does not simply stop for no reason, is that space treats every location alike. Rotational symmetry, the fact that the laws do not depend on which way you face, gives you the conservation of angular momentum, the reason a spinning skater keeps spinning, the reason planets keep orbiting. And time symmetry, the fact that the laws of physics are the same today as they were yesterday and will be tomorrow, gives you the conservation of energy. I want you to stop and feel the weight of that last one, because it is one of the most quietly astonishing facts I know. The reason energy is conserved, the reason you cannot create it from nothing or make it vanish into nothing, the reason that every scheme for a perpetual motion machine ever dreamed up is doomed before it begins, the reason you grow tired when you run and must eat to keep going, all of it traces back to a single fact about time. The laws of physics do not change from one era to the next. That is the whole reason. If the laws of physics were different today than they were yesterday, energy would not be conserved. The unbreakable accounting of energy that governs every engine, every star, every living cell, is not a separate rule we discovered by experiment and then had to take on faith. It flows directly and inevitably out of the steadiness of time itself, as surely as water flows downhill. The constancy of the law in time is the conservation of energy. They are the same fact, seen from two sides. The first time that truly lands on you, it is difficult to shake. A law you thought was about machinery turns out to be a statement about the even-handedness of time. And Noether proved this not just for these three familiar examples, but for any symmetry of any Lagrangian whatsoever. Every symmetry yields a conservation law. Every conservation law comes from a symmetry. So when physicists talk about the symmetries of the Standard Model, understand that they are not talking about decoration or aesthetics. They are talking about the scaffolding that holds the entire structure together. But the standard model has more symmetries than just the obvious ones of space and time. It has additional symmetries, hidden ones, internal ones. These are symmetries that do not involve moving through space or waiting through time at all. Instead, they involve transforming the abstract mathematical fields that describe the particles in ways that have no simple picture in everyday life. And here is the part that still amazes me every time I think about it. These internal symmetries are what dictate the forces. Let me try to give you a feeling for it with an imperfect picture. Imagine a compass needle that points north. Now imagine that you were allowed to redefine what north means, separately and independently, at every single point in space. North could mean one thing where your left hand is, and something completely different, where your right hand is, different again at your head and at your feet, different here and different a mile away, with no two places forced to agree. If you demand that the laws of physics still work out the same way, even after all those independent local redefinitions, something remarkable is forced upon you. You cannot make it work with the original ingredients alone. You are compelled to introduce a brand new field, a new particle, whose entire job is to reconcile the mismatches, to carry information from one point to the next so that everything stays consistent despite the local changes. And that new field, the one forced into existence by the demand for local symmetry, is the force carrier. The photon exists because of a symmetry of exactly this kind. The gluons exist because of a symmetry. The W and Z particles exist because of a symmetry. The forces of nature are not arbitrary additions to the world. They are required, demanded, compelled into being by abstract mathematical symmetries. The particular symmetries of the standard model go by a compact code, written as SU 3 times, SU 2 times, U on. And while those symbols need not concern you, what they stand for should take your breath away. The forces that hold the world together are consequences of symmetry. And once you have seen that, you cannot unsee it. But it raises a dangerous temptation, a misunderstanding that I have watched even very intelligent people fall into, and before we go any further, I have to clear it away. Because knowing the equation that governs everything is not at all the same thing as being able to predict everything. And the difference between those two is where the next part of our story begins. I want to return to the conservation of energy once more, because I think most people carry it around as a dry rule from a textbook, and they have never been shown the wonder hidden inside it. You have been told, since you were a child, that energy cannot be created or destroyed, only transformed from one form into another. It is presented as a brute fact about the world, something you simply have to accept. But Noether's theorem reveals that it is not a brute fact at all. It is a consequence of something even simpler and stranger, the fact that the laws of physics do not care what time it is. Run an experiment today, run it again in 1,000 years, and the laws governing it are identical. That sameness through time, that loyalty of the universe to its own rules, is the true source of the conservation of energy. The two are not separate facts that happen to both be true. They are one single fact, viewed from two angles. Sit with what that implies, because it reaches further than it first appears. If you could somehow find a place or a time where the laws of physics were quietly changing, drifting from one moment to the next, then in that place energy would not be conserved. You could, in principle, build a machine that drew energy from the drift itself. The reason no such machine has ever worked, the reason every inventor who ever promised free energy from nothing has failed, is not a limitation of their cleverness. It is that the laws of physics, as far as we can tell, hold perfectly steady through time, and so the energy books always balance, everywhere, always. Every engineer who has ever cursed the impossibility of perpetual motion was, without knowing it, bumping up against the even-handedness of time. There is a kind of quiet grandeur in that. The most practical rule in all of engineering, turns out to rest on one of the most abstract truths about the structure of reality. And the same logic, extended into the abstract internal symmetries I described, is what conjures the forces themselves into being. This is the part that took physicists the longest to absorb, and that, I think, is the true jewel of the whole Standard Model. The demand that a certain symmetry hold not just everywhere at once, but independently at every separate point in space and time, is so strict, so nearly impossible to satisfy, that the only way the universe can meet it is to introduce a new field whose entire purpose is to patch the seams. That new field is a force. The electromagnetic force, the strong force, the weak force. All three are the universe's response to the demand for local symmetry. They are not arbitrary furniture that happens to be in the room. They are required by the geometry of the rules themselves, as inevitable as the conservation laws, and just as beautiful. Part 9. Knowing the rules is not the same as winning the game. There is a misunderstanding I want to clear away before we go any further, because it trips up almost everyone who first hears that there is one equation behind the world. People hear the phrase one equation that describes everything, and they leap to a conclusion that seems perfectly reasonable but is completely wrong. They assume it means we can predict everything, that if we truly have the fundamental law, then we ought to be able to calculate the weather next Tuesday, or what you will choose to eat for lunch tomorrow, or whether a particular radioactive atom will decay in the next 5 minutes. And I understand why that feels like it should follow. If you know the rule that governs every particle, surely you can compute the future of any collection of particles you like. But it does not work that way, for two separate and profound reasons, and understanding why is essential to understanding what kind of thing the Standard Model actually is. Let me give you an analogy that I think makes the first reason vivid. Imagine you know the complete rules of chess, every one of them. You know how each piece moves, what counts as a legal move, what constitutes check and checkmate, how the game begins and how it can end. You possess, in full, the entire rulebook. Now, does knowing all of that mean you can defeat a grandmaster? Of course not. Anyone who has ever played chess knows that the gap between knowing the rules and mastering the consequences of the rules is enormous, perhaps unbridgeable for most of us. The rules are simple and finite. The consequences of the rules are an ocean without a visible shore. Knowing how the pieces move tells you almost nothing about how to actually win, because the number of possible games is beyond astronomical. Physics has exactly the same character. We know the Lagrangian, we know the equation, but solving that equation for a system made of many particles is, in the overwhelming majority of cases, staggeringly difficult, and very often it is impossible in practice. Let me give you a concrete sense of just how quickly it becomes hopeless. Take a single atom of iron, one atom. It has 26 electrons swarming around its nucleus, each one influencing all the others through the electromagnetic force. The quantum equations describing that one little atom, with its 26 interacting electrons, are essentially impossible to solve exactly by brute force. We need clever approximations and enormous computers just to get close. And you want me to predict the weather? The weather involves something like 10, followed by 25 zeros worth of particles, all interacting at once, all influencing one another from one instant to the next. Asking the fundamental equation to predict that is not asking too much of the theory. The theory is perfectly correct. It is asking too much of any computer that could ever be built. This is not a failure of physics. It is a practical limit on calculation, and the two are entirely different things. The equation is right. We simply cannot compute fast enough to follow all its consequences. But there is a second reason, and this one cuts even closer to the bone, because it is not about practical limits at all. It is built into the fabric of reality itself. In quantum mechanics, there is genuine randomness. Not the apparent randomness of a coin flip, which only looks random because we cannot track every detail of the toss, but a true, irreducible randomness that no amount of knowledge could ever remove. When a radioactive atom decays, there is no hidden clock ticking away inside it, secretly counting down to the moment of decay. There is no concealed mechanism that, if only we could see it, would tell us exactly when the atom will break apart. The decay is, at the most fundamental level, unpredictable in its timing. The equation does not give you the moment of decay, it gives you the probability of decay. It tells you that over a certain span of time, there is a certain chance the atom will decay, and that is all it tells you, all it can tell you, all that there is to be told. The certainty simply is not there to be found. Put those two facts together, and you arrive at something humbling and, I think, strangely freeing. Even with the perfect equation in hand, and even with a computer of infinite power and infinite speed, you still could not predict everything. The practical impossibility of the calculations would be lifted by the infinite computer, yes, but the genuine quantum randomness would remain, untouched, woven into the bottom of things. The future is not sitting there, fully written, waiting for a fast enough machine to read it out. The law is total, and yet the future stays open. So, when I tell you we have the equation that runs the universe, please do not hear me saying that the universe is a machine grinding out a predetermined story. The equation governs the probabilities, the tendencies, the underlying structure. It does not dictate every detail of what will happen, and it never could. And this is no mere technicality. It is a clue to something extraordinary about how reality is actually built at its foundations, a strangeness far greater than mere unpredictability, which is exactly where I want to take you next. There is a famous old dream in physics that this strangeness finally kills, and it is worth naming so that you can feel it die. 2 centuries ago, a great mathematician imagined a great intelligence that knew the exact position and motion of every particle in the universe at a single instant. Such an intelligence, he argued, armed with the laws of physics, could compute the entire future and the entire past with perfect certainty. Nothing would be hidden from it. The future would be as fixed and readable as a book already written, merely waiting to be turned page by page. For a long time, that vision seemed to be the logical end point of physics. If the world obeyed exact laws, then the world was, in principle, a machine whose every future state was already determined. Quantum mechanics demolishes that dream at its foundation, and not because we lack information, but because the information is not there to be had. The radioactive atom that may or may not decay in the next minute is not concealing a decision it has already made. There is no fact anywhere in the universe about exactly when it will decay until it decays. The most complete possible knowledge of the atom, every truth there is to know about it, still leaves the moment of decay genuinely open. So even the great calculating intelligence of that old dream, even with perfect data and infinite speed, would find itself unable to read the future, because the future is not yet written, not even in principle. The universe runs on exact laws and remains genuinely unfinished at every instant. I find that, far from being a disappointment, strangely consoling, the law is total, and the story is still open, both at once. Part 10. The particle that takes every path at once. I want to take you now into the strangest and, to my mind, the most beautiful idea in all of physics, and it grows directly out of the principle of least action we began with. So let me return to that thrown ball, and then replace it with something much smaller, and watch what happens to the whole picture. In the classical world, the ball follows a single path, the one that makes the action smallest. We have been through that. One ball, one path, the most economical route from start to finish. But now, forget the ball. Picture instead a single electron, that tiny particle from the center of the atom. It begins at one point, call it point A, and sometime later it arrives at another point, call it point B. In the everyday way of thinking, it travels along one route from A to B, the classical path, the path of least action. But that is not what actually happens. What actually happens is so much stranger that it took the genius of the 20th century to accept it. Imagine the electron leaving point A. It does not choose a single route to point B. Instead, it sets out along every possible route at once, every single one. A straight line across, a wide looping curve, a frantic zigzag that changes direction 1,000,000,000,000 times. A path that wanders out to the Andromeda galaxy 2.5 million light-years away and comes all the way back to arrive at point B on schedule. Every route you could imagine, and infinitely many you could not, the electron travels all of them simultaneously. Each path contributes a tiny arrow, a little quantity that points in some direction, and to find the chance that the electron gets from A to B, you add up all those tiny arrows from all the infinitely many paths. This is called the path integral, the sum over every possible history. And from this almost insane instruction, sum over everything that could possibly happen, the real world emerges, exactly as we measure it. Here is the beautiful part, the part that rescues sanity from the madness. For most of those wild paths, the tiny arrows point in essentially random directions. The arrow from the path that swings out to Andromeda one way very nearly cancels the arrow from a path that swings out almost the same way but returns by a slightly different route. Across the great mass of crazy, looping, wandering paths, the arrows point every which way and cancel each other out almost perfectly, leaving nothing behind. Only in one special region do the arrows fail to cancel. Near the classical path, the path of least action, the nearby routes all have arrows that point in nearly the same direction. There, and only there, the arrows reinforce one another, adding up instead of cancelling. So when you finish the enormous sum, the total is overwhelmingly dominated by the contribution from the neighbourhood of that one classical path. The infinity of strange routes erases itself, and what survives is the single sensible trajectory. That is why, in everyday life, things appear to follow one path. The ball seems to trace one clean arc through the air, because the ball is heavy, and for a heavy object, the cancellation of all the far-out paths is so utterly thorough that only the single action-minimizing path survives the sum. But for something as light as an electron, the cancellation is not quite so complete. The electron genuinely explores many paths. It really does, in a sense we can measure, go more than one way at once. And I want to be very clear that this is not philosophy, not a poetic way of speaking. It has consequences, you can see. The most famous of them is an experiment so simple in its setup and so shattering in its implications that it has become the very emblem of quantum strangeness. It is called the double-slit experiment. And once you understand it, you understand why physicists talk the way they do about reality. Here is what you do. You take a barrier with two narrow slits cut into it, side by side, and behind it you place a screen. Then you fire electrons at the barrier, one at a time. Just one electron in the apparatus at any given moment, so there is no possibility of one electron bumping into another. Each electron passes through and lands somewhere on the screen, leaving a small mark. At first, the marks seem to arrive at random, one here, one there, scattered across the screen, like the first drops of rain on dry pavement. But you are patient. You have all night. And as the marks accumulate, hour after hour, something impossible begins to take shape. The dots are not scattering evenly. They are arranging themselves into a pattern of bright bands and dark bands, stripes of many electrons alternating with stripes where almost none ever land. It is an interference pattern, the exact signature you see when two waves overlap, bright where the waves add together, dark where they cancel. But you sent the electrons one at a time. There was never more than one in the machine. There was nothing for it to interfere with except itself. Its quantum wave, its collection of arrows from all possible paths, went through both slits at once, and the paths through the left slit interfered with the paths through the right slit, some adding and some cancelling, building the striped pattern one lonely electron at a time. And then comes the final twist, the one that unsettles me no matter how many times I sit with it. If you place a small detector at one of the slits, just to peek, just to catch which slit each electron really goes through, the interference pattern vanishes. The stripes dissolve into two dull smudges, exactly what you would expect if each electron simply went through one slit like a sensible little pellet. The mere act of finding out which path was taken collapses the sum over all paths and forces the electron to commit to one. It takes every path until you look, and then it takes only one. That is quantum mechanics in its starkest form, and notice what it does to the principle we started with. The principle of least action, which seemed in the classical world like such a strange, almost mystical idea, nature surveying all paths and choosing the best, turns out to be no mysticism at all. It is simply what the quantum sum over all paths looks like when you stand far enough back, when the object is heavy and the cancellation is complete. In quantum mechanics, all paths genuinely contribute. In classical mechanics, only the path of least action survives the cancellation. Nature is not minimizing anything on purpose. There is no foresight, no surveying, no choosing. There is only the sum over every history, which, viewed from the scale of balls and planets, automatically concentrates itself around the single classical path. The principle of least action is not a separate law handed down from above. It is a consequence of quantum mechanics, the large-scale shadow cast by the strangeness underneath. And that, to me, is one of the most profound things in all of physics, the moment where the everyday world is revealed as the leftover residue of something almost unimaginably stranger. But I still owe you the fourth and final thing the great equation must do, the last piece that was discovered, the one that explains why anything in the universe has mass at all. Let me hold you inside the double-slit experiment a little longer, because I do not think you can sit with it too long. Picture yourself in a darkened room, watching that screen through a long night. The electrons arrive one at a time, with long pauses between them, each one hitting the screen at a single, definite point, leaving a single, definite mark. Nothing about any individual electron looks wave-like. Each is a particle, arriving as a particle, landing as a particle, a small, certain dot in the dark. And yet, you cannot predict where the next dot will fall. All you can say is where dots are likely and where they are unlikely. And as the hours pass and the dots accumulate by the thousands, the likelihood reveals itself as a pattern of bright stripes and dark gaps, a pattern that can only be explained if each lonely electron somehow passed through both slits at once and interfered with itself on the way to the screen. The particle is real. The wave is real. They are the same thing, seen from two sides, and the experiment forces both truths upon you at once. And then there is the part I find almost unbearable, the part about looking. Place a detector at one slit so that you can know which way each electron went, and the stripes vanish. Not gradually, not partially. They are simply gone, replaced by the two dull blobs you would expect from ordinary particles. The only thing you changed was whether the information about the path existed in the world. You did not touch the electrons more roughly. You did not block a slit. You merely arranged for the universe to contain a record of which way each one went, and that alone was enough to erase the interference. The act of the path becoming knowable changes what actually happens on the screen. I have worked with this for a lifetime, and I still cannot make it feel ordinary. It tells us that the sharp, single-pathed world we think we live in is not the fundamental one. The fundamental world is the sum over every path, and the single path is only what is left when knowledge forces the sum to collapse. When you carry that lesson back to the principle of least action, the whole night reorganizes itself around it. We began with a ball that seemed to choose out of all possible paths, the one of least action, and I called that strange and almost mystical. Now you can see that there is no choosing at all, and no mysticism either. The ball, like the electron, in some sense takes every path. But the ball is so heavy, and the paths so thoroughly cancel one another, that only the single path of least action survives to be seen. The orderly classical world, the world of definite trajectories and predictable arcs, is the residue left behind after the quantum sum has cancelled almost everything away. The everyday is the exception, not the rule. The strangeness is the foundation, and the ordinary is what is left over. Part 11. The field that fills empty space. I told you that the standard model Lagrangian does 4 things. It tells you what particles exist, what forces exist, how they interact, and how the particles get their mass. We have walked through the first 3. Now I owe you the 4th, and it is special, because it was the last piece to be discovered and the hardest to confirm, and because it solves a problem that you would never have guessed was lurking inside everything we have said so far. Here is the problem. Those beautiful symmetries I described, the ones that dictate the forces and give the theory its elegance and its mathematical soundness, carry a hidden and disastrous implication. If you take those symmetries at face value, they demand that all the particles be massless. Every one of them. The photon, the electron, the quarks, the W and Z particles, all of them should have exactly 0 mass, and all of them should travel at the speed of light. And that is plainly, obviously wrong. The electron has mass. The quarks have mass. The W and Z particles are extremely heavy, around 80 and 90 times the mass of a proton. The world is full of massive things moving far slower than light. So something has to break the symmetry. Something has to give these particles their mass. But you cannot break the symmetry crudely, because if you do, you destroy the very consistency and mathematical health that the symmetry was providing. You have to break it gently, delicately, in a way that gives the particles mass without wrecking everything else. The mechanism that accomplishes this is one of the most remarkable ideas in physics, and at its center is a field that fills all of space. Let me ask you to come with me into the emptiest place you can imagine. Picture the void between the galaxies, millions of light years from the nearest star, where there are no atoms, no light, nothing at all that you would ordinarily call a thing. By every common sense measure, that region is perfectly empty, and yet it is not. Threaded through it, lying over every cubic inch of that emptiness, is a field whose value is not 0. Even in the most absolute vacuum, even where there is nothing else whatsoever, this field is switched on, holding a steady, non-zero value everywhere, like an invisible medium soaking all of space. We call it the Higgs field, and the reason it matters is what it does to particles that try to move through it. When a particle travels through the Higgs field, it interacts with it, and that interaction is what we experience as the particle having mass. A particle that interacts strongly with the field feels heavy and is hard to push, because the field resists its motion. A particle that interacts weakly with the field feels light. And a particle that does not interact with the field at all, like the photon, has no mass whatsoever, which is precisely why the photon sails through the universe at the full speed of light, never slowing, never dragging, untouched by the field that weighs everything else down. Now, every field in the standard model has a particle associated with it, a ripple in the field that is the field's smallest possible disturbance. When you disturb the electromagnetic field just right, you get a photon. When you disturb the surface of a pond, you get a wave. And when you disturb the Higgs field just right, you get a particle called the Higgs boson. The Higgs boson is the ripple in the Higgs field, the visible proof that the field is really there. The whole idea was proposed in the 1960s by Peter Higgs and by several others working at the same time, and for nearly 50 years it remained the one piece of the Standard Model that had never been directly confirmed. The theory predicted that the Higgs boson should exist, and it predicted, roughly, how heavy it ought to be. But to actually create one, to disturb the Higgs field hard enough to shake loose a single ripple, you needed to reach energies that no machine on Earth could produce. So the world waited. For decades, the great particle colliders climbed toward higher and higher energies, and the Higgs boson stayed just out of reach, predicted but unseen, the last missing brick in the wall. And then, in the year 2012, at the Large Hadron Collider at CERN, the same laboratory that had found the W and Z particles 30 years earlier, the energies were finally high enough, and there it was. The Higgs boson, appearing in the detectors at a mass of around 125 times the mass of a proton, just where the theory said it should be. The last piece of the Standard Model fell into place. The equation was complete. After a century of work, the recipe for the particles, the forces, the interactions, and now the origin of mass was finished and confirmed. So you might think, surely now the story is over, and we can rest in our triumph. We have the complete equation. We have tested it to 12 decimal places. We have found the very last particle it predicted. What more could there possibly be? And if that were the whole truth, I would not have warned you that this equation keeps me awake at night. I would not have promised you, at the very beginning, that something enormous is missing, because here is where the trouble begins in earnest. The Standard Model, for all its glory, for all its precision, for all its hard-won completeness, is not the whole story. It is not even close. And the things it leaves out are not small, obscure, technical details that only a specialist could care about. They are enormous, gaping holes, and through them you can see most of the universe. Let me show you the holes now, one by one, and you will understand at last why the most successful equation ever written is also, in a sense, a confession of how little we know. I want to make sure the idea of mass from a field does not stay abstract, because it is one of the most genuinely surprising things we have learned about the world. We usually think of an object's mass as simply how much stuff is in it, a property the object carries entirely within itself. But the Standard Model tells a stranger story. A fundamental particle, like an electron, has no mass of its own to carry. Left to itself, by the logic of the symmetries, it would race along at the speed of light, weightless. It has mass only because of how strongly it interacts with the Higgs field that fills the space it moves through. Take away the field, and the mass goes with it. The heaviness of matter is not a thing matter possesses on its own. It is a relationship between matter and the invisible field, soaking all of space. The solidity of the world, in this picture, is borrowed from the vacuum. And notice the elegant logic of why the photon is different. The photon does not interact with the Higgs field at all, and so it has no mass, and so it can never slow down below the speed of light, not for an instant. This is not a separate fact you have to memorize. It falls straight out of the same mechanism that gives the electron and the quarks their mass. One idea, the Higgs field with its non-zero value everywhere, explains both why most particles are heavy and why light is weightless and eternal. When the Higgs boson was finally found in 2012, after nearly 50 years of searching, what was being confirmed was not merely the existence of one more particle, it was this entire picture of where mass comes from. The discovery was a vindication of one of the strangest ideas physics had ever dared to propose, that the weight of everything you have ever lifted is, in the end, a property of empty space. Part 12. 5%. Let me show you what the equation leaves out, and I will start with the most glaring omission of all, the one you may have noticed yourself. We have spent the whole night talking about forces, and I named 4 of them at the start: gravity, electromagnetism, the strong force, and the weak force. But the Standard Model, that magnificent equation on the coffee mug, describes only 3 of them. Electromagnetism, the strong force, and the weak force are all there, woven into the recipe. Gravity is not. Gravity is nowhere in the equation at all. The Standard Model Lagrangian says nothing whatsoever about why an apple falls from a tree, nothing about why the planets circle the sun, nothing about why galaxies hold themselves together. The most familiar force in your daily life, the one you feel in your body every second of every day, is simply absent from our most fundamental law of matter. Gravity is described, and described beautifully, by an entirely separate theory, Einstein's general relativity, which says that gravity is not really a force at all, but the curving of space and time in the presence of mass and energy. And general relativity works wonderfully on its own for the large things, for planets and stars and galaxies and the universe as a whole. But here is the agonizing problem. We do not know how to combine the 2 theories. When physicists try to write a quantum theory of gravity, the way we have quantum theories of the other 3 forces, the mathematics simply falls apart. You get infinities pouring out of the equations, infinities that cannot be tamed or removed by the usual tricks that work everywhere else. The 2 great theories of physics, the Standard Model for the very small and general relativity for the very large, are written in different mathematical languages, built on different principles, and when you try to force them to speak to each other, you get nonsense. It is as if we had 2 perfect maps of the same city, drawn to different scales in different projections, and every time we tried to lay one over the other, the streets refused to line up. Something is missing, some more profound understanding we simply do not yet possess. That is the first hole. Here is the second. When astronomers measure how fast the stars at the edges of galaxies are moving, they find something profoundly alarming. The stars are moving far too fast. Based on all the visible matter in those galaxies, all the stars and gas and dust we can actually see, there is nowhere near enough gravity to hold those fast-moving outer stars in place. They should be flung off into intergalactic space like mud off a spinning wheel. But they are not. They stay. Something invisible is holding them, something that has mass and exerts gravity, but gives off no light and interacts with light not at all. We call it dark matter because we cannot see it, and it is not some minor correction. There is roughly 5 times more dark matter in the universe than ordinary matter. 5 times. Everything you have ever seen, every star and planet and person, every atom, the Standard Model so beautifully describes, amounts to only about 1/6 of the matter in the cosmos. The rest is dark, unseen, unknown. And the Standard Model contains no particle that could possibly be it. Nothing in the equation accounts for it at all. And here is the third hole, the largest of them all. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down, as everyone had expected, but speeding up. The galaxies are flying apart faster and faster as time goes on, as though some unknown energy were pushing all of space outward, an energy that fills the vacuum itself and drives a kind of cosmic repulsion. We call it dark energy, and we have almost no idea what it is. Worse still, it is not a minor ingredient. Dark energy is the single largest component of the universe, making up around 70% of the total energy content of everything that exists. And the Standard Model does not explain it. It does not even mention it. So let me add this up for you, slowly, because the total is the thing that, if you let it, will keep you up at night, as it does me. The Standard Model, the most precisely tested theory in the history of science, accurate to 12 decimal places, the crowning achievement of a century of genius, beautifully and completely describes about 5% of the energy content of the universe. 5%. The ordinary matter, the atoms, the things we can see and touch. The other 95%, the dark matter and the dark energy, lies entirely outside the equation, unexplained, unaccounted for, unknown. Everything our greatest law describes is a thin, bright film floating on the surface of something enormous and dark that we cannot yet name. If that does not unsettle you, sit with it a moment longer, because it should. We wrote down the law of the universe and discovered, when we looked up, that it governs only a small corner of it. And even within that 5%, even in its own home territory, the Standard Model has strange features that cry out for an explanation it cannot give. Why are there 3 generations of matter particles, 3 copies of the basic pattern, when everything you see is built from only the first? The equation does not say. You simply put the number 3 in by hand. Why do the particles have the particular masses they have? Why is the electron about 2,000 times lighter than the proton? The equation does not predict those masses. You have to go and measure them and then plug them in. In all, there are around 19 numbers in the Standard Model that the theory cannot derive at all, numbers that must be determined by experiment and inserted by hand, and nobody knows why they take the values they do. There is the puzzle of why the universe is made almost entirely of matter. When the equation says matter and antimatter should have been created in nearly equal amounts in the early universe and then annihilated each other completely, leaving nothing behind to build stars and planets and people. And there is the matter of the neutrinos, those faint particles which the original Standard Model assumed were completely massless, until experiments proved that they do, in fact, have a tiny mass, forcing us to patch the equation with new pieces it did not originally contain. So even the equation on the coffee mug is, strictly speaking, already out of date. The most successful theory ever written is incomplete, provisional, and openly confessed by its own authors to be a beautiful fragment of some larger truth we have not yet found, which raises the only question that matters now. What is the larger truth? And how would we ever find it? Let me say the matter and antimatter problem more plainly, because it is one of the quietest and most disquieting of the wholes. For every kind of particle, there is an antiparticle, a sort of mirror image with the opposite electric charge. When a particle meets its antiparticle, the two annihilate each other completely, vanishing in a flash of pure energy. Now, the Standard Model says that in the first moments of the universe, matter and antimatter should have been created in almost exactly equal amounts. But if that were the whole story, then all of that matter and antimatter should have found each other and annihilated long ago, leaving a universe filled with nothing but light, and no atoms, no stars, no planets, no us. Yet here we are. The universe is built almost entirely of matter, with its antimatter partner mysteriously absent. Some tiny imbalance must have tipped the early universe toward matter, and the Standard Model does contain a faint hint of such an imbalance, a subtle lopsidedness in the weak force. But when you do the arithmetic, that known imbalance is nowhere near large enough to explain why anything exists at all. The reason there is something rather than nothing is, quite literally, an open problem. I want you to feel the full force of the 5% reckoning, because everything we have built tonight has been leading here. We have followed the principle of least action from a thrown ball to the most precise equation ever written. We have watched it absorb light, the weak force, the strong force, and the origin of mass. We have seen it predict the magnetism of the electron to 12 decimal places. And when we finally lift our eyes from the equation and look out at the universe it was meant to describe, we find that it accounts for about 1 part in 20 of what is actually there. The stars, the planets, the gas, the dust, every atom the equation so beautifully governs, all of it together is a thin and shining film on the surface of a cosmos whose overwhelming bulk, the dark matter and the dark energy, we cannot name, cannot see, and do not understand. We lit a single candle and discovered, by its light, the size of the dark room around us. That is not a reason for despair. But it is a reason for humility, and it is, if you let it be, a reason to lie awake. Part 13. The Impossible Dream and the Last Line Not Yet Written. So here we stand, at the edge of what we know, and I want to be honest with you about what lies beyond it, including how little of it we can see. We have the most successful equation in the history of science, and it describes 5% of the universe. We have a magnificent theory of gravity that refuses to make peace with the quantum world. We have 95% of everything sitting in darkness, in the form of dark matter and dark energy we cannot explain. And we have a fistful of unexplained numbers we simply measured and wrote down. This is what I mean by the impossible dream. The dream is to find one equation, truly one, that describes everything, not almost everything, not everything except gravity, not everything except the dark 95%, everything. One recipe, one principle of least action, one law for all four forces and all the particles, the visible and the dark alike. And the plain truth is that we are not there. We may not even be close. People have tried, and tried magnificently. There are proposals called grand unified theories, which attempt to merge the three forces of the Standard Model into a single, larger symmetry, the way the electroweak theory merged two of them. There is an idea called supersymmetry, which proposes that every particle we know has a heavier, undiscovered partner, doubling the cast of characters in exchange for a great gain in mathematical elegance, and, as a bonus, a possible candidate for dark matter. There is string theory, perhaps the most ambitious of all, which proposes that the particles are not points at all, but tiny vibrating strings, with different patterns of vibration corresponding to different particles, and that there are extra dimensions of space curled up too small for us ever to see directly. And there is loop quantum gravity, which tries to quantize space itself to make space-time grainy and discrete at the very smallest scales. These are fascinating ideas. Some of them are genuinely beautiful. A few of them even make predictions, but not one of them has been confirmed by experiment. Not one. And in physics, there is one rule that has never once bent, no matter how lovely the theory or how brilliant its author. If your theory does not agree with experiment, it is wrong. That has always been the rule, and it always will be. Beauty is not evidence. Elegance is not proof. The real world has the final say every time. So what is the right attitude to hold, standing here? I think it is two things at once, held in balance. We should be proud, genuinely proud, of what we have built. The Standard Model is one of the supreme achievements of the human mind, the work of centuries and of thousands of brilliant people. It captured real and lasting truths about nature, the discovery that symmetry dictates the forces, the discovery that empty space has structure, the discovery that particles are ripples in fields that fill all of space. Those are permanent insights, and no future theory will erase them. But we should also be ruthlessly honest about what we do not know, and we should never let the beauty of our equations seduce us into mistaking them for the truth before the experiments have spoken. I have watched fine physicists fall in love with their own theories and slowly lose touch with the evidence, and it is a quiet kind of tragedy. Physics is not mathematics. Physics is about the real world, and the real world is under no obligation to match our sense of elegance. And yet there is real reason for hope, and it comes from the pattern we have watched all night. Every single time someone has successfully unified two things that looked separate, the result was simpler and more beautiful than anyone expected, and it gave back more than was put in. Maxwell unified electricity and magnetism, and received light as a gift nobody had ordered. Einstein unified space and time and discovered, as a consequence, that mass and energy are the same thing. The electroweak theory unified electromagnetism and the weak force and predicted the W and Z particles into existence before anyone had seen them. The theory of the strong force predicted that quarks could never be pried apart and isolated, and that prediction held. So the pattern is clear and it is encouraging. Unification works, and it pays you back with interest. That suggests, though it does not promise, that a more profound unification is still possible, that somewhere beneath the Standard Model and general relativity there waits a single structure from which both of them fall out as consequences, the way light fell out of Maxwell. Nature does not owe us that. Nature does not owe us simplicity or elegance or a final answer at all. It could be that the bottom of things is messy or endless, an onion of further and further layers with no final core. We do not know, and the only honest answer is that we do not know. But not knowing is not the same as having no hope. Not knowing is where the adventure begins. I sometimes like to imagine that nature is an enormous game of chess played by the gods, and that we are only spectators who arrived after the game had already started. We do not know the rules. We were never told them. We do not even know all the pieces. But by watching, patiently, carefully, over centuries, we begin to work out the rules for ourselves. We see a bishop always moving along the diagonals, and we say, "There, I think I have found a rule." We see a knight make its strange bent leap, and we say, "That is a different rule, a stranger one," and piece by piece, move by move, we assemble our understanding of the game. And here is the wonderful thing about it. Every rule we work out lets us predict the next move a little better, and when our prediction comes true, we feel a rush of joy because we have understood something real. But when our prediction fails, when the gods make a move no rule of ours allows, we feel an even greater excitement, because it means there is a new rule we have not yet found, a hidden layer of the game waiting to be uncovered. That is the true spirit of physics. It was never really about reaching the final answer. It was always about the searching itself. So let me leave you, as the night settles, with one last thought to carry into sleep. The principle of least action, the idea that began our whole journey, has a curious and fitting secret hidden in its name. It is not truly a principle of least action at all. More precisely, it is a principle of stationary action. The path nature takes is the one for which the action does not change, to first order when you wiggle the path ever so slightly. Usually that means the smallest action, a minimum, but not always. Sometimes it is a kind of balance point, a saddle. The old name is a little imprecise, but the idea beneath it is exact, and it carries a strange and lovely flavour. It suggests that the laws of nature can be written as a single statement about what is made stationary, what is optimized, as though the entire universe were the solution to one enormous mathematical problem. Whether that is a profound truth about reality itself, or merely a reflection of the way our particular kind of mind likes to organize what it sees, I honestly do not know. But I find it beautiful, and I find it reason enough to keep searching, because the equation on the coffee mug, for all its precision and all its glory, is not the last word. The last word has not been written. And somewhere, perhaps tonight, perhaps in a room not far from where you are resting, some young person is staring at a physics problem, or an experimental result that does not quite fit, or a pattern in the mathematics that no one has noticed before, and they are about to see something that no human being has ever seen. They are about to find the next piece of the puzzle. And when they do, the picture of the universe will shift again, the way it has shifted so many times before, becoming stranger and larger and more beautiful than any of us imagined. That these 3-pound knots of neurons inside our skulls, which evolved on an African plain only to help our ancestors avoid being eaten, can reach out and read the architecture of reality at all, can write one equation that predicts the magnetism of an electron to 12 decimal places may be the most astonishing fact in this entire story. The universe is comprehensible, and we, somehow, are built to comprehend it. The rest of the equation is still out there, waiting. And I, for one, cannot wait to see what it says. I want to be careful not to leave you with the impression that the Standard Model is broken, because it is not. It is not wrong. Within the territory it claims, it is correct, magnificently so, confirmed to a precision that no other theory in any science has ever matched. The point is not that it is mistaken. The point is that it does not go far enough. It is like a map that describes one city perfectly, every street, every corner, every alley, rendered with flawless accuracy, but which simply goes blank beyond the city limits. The map is not lying. It is just not finished. And I have come to think that this is not a tragedy, but a gift, because it means the work is not over. There is more to find. There are more surprises waiting in the blank spaces past the edge of the map. If we already held the final and complete theory of everything in our hands, the great adventure of physics would be finished. And for someone who lives for the joy of understanding one more piece of nature, that would be the saddest news imaginable. The incompleteness is what keeps the door open. There is a reason I keep returning to the image of the gods playing chess, and I want to give it to you fully before we close. We arrived in the middle of a game we did not start and were never taught. We do not know all the rules. We do not even know all the pieces. But we have been watching for a very long time, and patiently, move by move, we have worked out a great deal. We learned how the bishop of electromagnetism moves, and the knight of the weak force, and the strange castling of mass, and the Higgs field. Each rule we uncovered let us predict the next move a little better, and when our predictions came true, in the form of the W and Z particles, or the Higgs boson appearing right where the mathematics said it would, we felt the particular joy that comes only from understanding something real about the world. But the moves we cannot yet predict, the falling apart of gravity, the dark matter holding the galaxies, the dark energy pushing the cosmos open, those are not failures. They are the unexplained moves that tell us there are rules we have not yet found, hidden layers of the game still waiting. And the search for those rules is not a chore we endure on the way to some final answer. The search is the thing itself. It always was. So, as you let yourself drift tonight, carry one last thought down with you. The equation on the coffee mug is one of the most beautiful things our species has ever made, and it is not the last word. The last word has not been written, and perhaps it never will be, and that may be exactly as it should be. Somewhere out there, maybe close by, maybe in a quiet room with a single lamp burning, someone is looking at a problem that does not quite fit, a number that comes out wrong, a pattern no one has noticed before, and they are about to see a little further into the game than anyone ever has. When they do, the whole picture will shift, as it has shifted so many times before, growing stranger and larger and more beautiful than we can now imagine. That minds, like ours, evolved on an open plane merely to keep our ancestors alive, can reach out and read even 5% of the architecture of the universe, and read it to 12 decimal places, may be the most astonishing thing in this entire story. The universe is comprehensible. We are somehow made to comprehend it, and the rest of the equation is still out there, patient, unwritten, waiting for whoever is willing to keep looking.